The spring-loaded governor is shown in this figure. The two balls, each of mass 6 kg, are connected across by two springs. An auxiliary spring B provides an additional force at the sleeve through the medium of a lever, which pivots about a fixed center at its left-hand end. In the mean position, the radius of the governor bolts is 120 mm and the speed is 600 rpm. The tension in each spring is then 1 kN. Find the tension in the spring B for this position. When the sleeve moves up 15 mm, the speed is to be 630 rpm. Find the necessary stiffness of the spring B if the stiffness of each spring A is 10 kN per meter. Neglect the moment produced by the mass of the bolts. So this is the question. Okay. So we'll try to identify the given data first. A spring-loaded governor is shown in this figure. The two balls, each of mass 6 kg, right? So there's a ball, and here is another ball, each of 6 kg, are connected across by two springs, right? So they are connected across by two springs. There are two springs. An auxiliary spring B, right? Here's an auxiliary spring B, provides an additional force at the sleeve, right? Additional force at the sleeve through the medium of a lever, which pivots about a fixed point at the left hand end. So here is the fixed point of this lever at this left hand end. In the mean position, so here is the mean position. The radius of the governor body is 120 mm. Radius is given, it is 120 mm, and the speed is 600 rpm. Right, so at the mean position, the speed is 600 rpm. The tension in each spring is 1 kN. Right, so tension in these springs is 1 kN. Find the tension on this spring, right? Spring B. So all these data are given. Now we have to find the tension on this spring for this position, 600 rpm. Okay. And then part 2, when the sleeve move up 15 mm, right? So when the sleeve moves up 15 mm, speed is to be 630 rpm, right? So the speed need to be 630 rpm for the movement of the sleeve of 15 mm. So for that, we need to find the stiffness of the spring B. Spring B, this one is the spring B, right? And stiffness of each spring A is given as 10 kN per meter. Right? So this spring A, there are two springs, each of the stiffness 10 kN per meter. Okay, and also given next, neglect the moment of mass of the bolts, right? So due to the movement of the bolts, there would be some moment, we can neglect them. It is given in the version. So small m 6 kg, right? Mass of the bolt 6 kg. R is equal to R1 120 mm, right? So 120 mm. N is given for first position, it is 600 rpm. And from N, we can find the omega, that is 2 pi into 600 by 60, that is equal to 62.84 radian per second. Okay. Now we have to find the tension on the B for this particular position. Okay. And the lengths are given from B spring to the pivot point 160 mm, and B spring to the sleeve, it is 80 mm. Okay. And the lever arm, it's 90 mm. Ball arm is also 90 mm. Okay. Let's try to solve it. SB1 spring force on tension in spring B. Okay. So SB1 is the spring force on B. Mg is total load at the sleeve. Okay. So now we'll try to solve it. We know that the centrifugal force at the minimum speed, that is at this position, this is the minimum speed that is given. So we can find the centrifugal force Fc1 is equal to m1 r1 omega 1 squared. So m1 is given 6 kg, r1 is given 120 mm, that is 0.12 meter. Omega 1 squared, we now have found it to be 62.84. Right? So 62.84 whole square. From this, we can find the centrifugal force Fc1 is equal to 2843 Newton. Right? Since the tension in each spring A is 1 kN and there are two springs, therefore total spring force in spring A is 2 into 1, that is 2 kilonewton. Why? There are two springs, each of it exerting 1000 Newton, right? That is 1 kilonewton, and therefore it is 1000 into 2, 2000 Newton. Okay, so SA1, so spring force at A1 at minimum position is SA1 2000 Newton. FC1, centrifugal force at minimum position is 2843 Newton. So the resultant force is 843 Newton. Why? Centrifugal force is acting this way, spring force is acting this way. So centrifugal force is 2843 and spring force is 2000. So resultant is 843 this way. Okay, we'll have it. Now taking moments about the pivot point O. Right, so here is a pivot point O. We'll take moments. So we have C1, which is anti-clockwise, spring force clockwise, and mg, which is again clockwise. Okay. Therefore, FC1 into 90, FC1 into 90, the distance is 90, is equal to SA1 into 90, right? SA1, that is spring force into length 90 plus mg by 2, right? We are taking only half of the mass for the system, so mg by 2 into this length is also given, that is 90, right? So this length is also 90, right? So when you solve it, you will have this 90, this 90, this 90 will be cancelled out. So FC1 equal SA1 plus mg by 2. Right? FC1 is equal to SA1 plus mg by 2. Okay. So mg, which we have to found, right? Mg equal to, I will multiply this thing with 2. So 2 FC1 minus SA1. So minus 2 SA1. Right? If I multiply it with 2 FC1 minus 2 SA1. So that is equal to 2 into FC1 2843 minus 2 into SA1, that is 2000, right? So when you solve it, that is 1686 Newton, right? 1686 Newton. Right? So mg is given as 1686 Newton. Okay. Now we will take moments about Q. Why? Because we already know the mass or weight of the mass, right? We already know the weight of this mass at the sleeve, right? So we'll take moments about point Q. Why point Q? Because it is pivoted at this point. So based on this moment, we can take moments. SB1, so that is acting this way, right? SB1 into 160. So we know we are taking moments about point Q. So SB1 is anti-clockwise, right? If I taking moment about Q, spring force is anti-clockwise, and mass, it is clockwise. Why? Mass is acting downwards, and spring force will act upwards, right? So spring force SB1 into the length 160 is equal to mass mg, that is 1686 into this length, that is 160 plus 80, and that is 240, right? 160 plus 80, so that is 240. So when I solve it, SB1 into 180, that is SB1 spring force into 160 is equal to 404,640. Okay, and therefore spring force SB1 is equal to 404,640 divided by 160, which will give you 2,529 Newton. 2,529 Newton. So now we have found the answer for the part 1. The part 1 for the part 1 of the question is find the spring force at spring B for the given this position, right, which we have already found. Now the second one is we have to find the stiffness of the spring, right? Find the necessary stiffness of the spring B. For the stiffness of the spring B, we have, you can see the H. So H is this movement, right? H is this movement. So H is equal to 15 millimeter, which is given in the question, right? Sleeve moves up to 15 millimeter. Okay. N2 are 630 RPM, right? So that's the question. Omega 2. So omega 2 we can find 2 pi into 630 by 60. This is 66 radian per second. And SA, that is spring force 10 kilonewton per meter. Right? That is 10 into 10 to the power 3. 10 kilonewton. So stiffness is 10 kilonewton. That is 10 into 10 to the power 3. Let S be the stiffness of the spring B. So that this is what we have to find. Right? This is what we have to find. SB, stiffness of the spring B. At maximum position, first of all, let us find the maximum radius of rotation, R2. Right? So we have to find this R2 first, so that we can apply it in the equation. So to find R2, when the sleeve moves up by 0.15 meters, so when this one moves this way 15 millimeter up, we need to find how much is this distance, right? So we know H is equal to, this H is equal to R2 minus R1 into y upon x, right? R2 minus R1 into y upon x, right? So this is a common formula we are using. Why? Because if we take any angle here, this angle opposite over adjacent, or any of this angle is equal to this angle, right? So say for example you are taking a sine here, so opposite h upon hypotenuse 90 will be equal to sine of this angle opposite this upon hypotenuse this, right? So based on that we can derive a formula h is equal to r2 minus r1 into y upon x. So r2 can be written as r1 plus h into y upon x, right? So r1 is given 0.12, right? R1 that is given in the question 0.12, 12, right? 120 millimeter. So that is 0.12 into x upon y. Sorry, h into x upon y. H, it's given in the question, it's for 15 millimeter limit, 15 millimeter lift. So that is 0.015 into x upon y. We know x is 90, y is 90. So 90 upon 90, that is 1, right? So which means we are having this as the formula. Okay. So when you solve it, you will have 0.135 meter, right? Centrifugal force at the maximum speed. Now we can calculate the centrifugal force. The formation equation is FC2, that is centrifugal force at maximum. Usually we use this suffix 2 for the maximum speed. So FC2 is equal to m r2 omega 2 square, right? So m, that is 6 kilogram, right? It is given in the question. R2, right, that is 0.135 meter into omega 2 square. Omega 2 we have found that is 66 radian per second. So 66 square, which is equal to 3528 Newton, right? And the extension of the spring here, right? So now at the maximum position, the extension is R2, that is equal to 2 into R2 minus R1 into number of springs, right? So 2 into R2, that is 0.135, right? 0.135 minus R1, R1 which is given in the question, that is 0.12, right? 0.12, R2 minus R1 into number of springs, that is 2, right? So when you solve it, you will have 0.06 meter, right? So now the extension of spring A at this position is 0.06 meter, and the centrifugal force at this position is 3528 Newton, right? So when you apply these two things in the formula, okay, we have total spring force, that is initially it's 2000. Now we have extension 0.06 into the stiffness of the spring 10 into 10^3, that is 2600. So now SA2 stiffness spring force is found. We'll take a moment. Okay. So FC2, okay, FC2 into 90, FC2 here. Now at maximum position, this FC1 will change as FC2. We know that suffix will change as FC2 into 90 into equal to SA2, SA2, that is spring force at A, suffix 2 for maximum. So SA2 into again this and this 90 plus mg by 2 into 90, right? So this mg by 2 is the mass of weight at sleeve into the length 90. So when you solve it, you will have FC2 is equal to SA2 into mg by 2, right? So I will replace now with the known values. Mg is equal to, right? Mg is equal to 2FC2 minus 2SA2, right? 2FC2 minus 2SA2. 2 FC2, FC2 we have already found 3528 Newton, right? Centrifugal force at maximum, that is 3528 Newton, minus 2 SA2. SA2 also we have found 2600 Newton, right? 2600 Newton. So 2 into 3528 Newton minus 2 into 2600 Newton, which will give you 1856 Newton, right? So at this position, okay, at this position 630 rpm, the force at sleeve, which is the weight mg, is equal to 1856 Newton. Okay. Again, taking moments about point Q. So now we are going to take moments about point Q. Why? We need to find the stiffness of the bead, right? So we'll take moments about Q, right? Neglecting the moment produced by the mass of the balls. Why we are doing that? Because now you see the ball is this way. Okay, the ball is this way. So while we are taking moment about this point O, this mass or weight will act this way, and there's a distance, so we need to calculate it, right? But it is given in the question, we can neglect that, right? We can neglect that. So we are neglecting the effect of this mass because it is so small compared to rest of the forces. Okay, so we'll neglect this. So what we will have is an FC2, an SA2, an MG. Right? So these are three things we have. Okay. Also an SB2. Okay, so SB2, SA2, MG, and FC2. All right. So we will put them in the equation. SB2 into 160, right? So we are taking moments about point Q. So SB2 is anticlockwise, right? SB2 is acting this way from down to up, so that's anticlockwise. So SB2 into 160 will be equal to mg, right? Mg into the length of mg is 160 plus 80, right? 160 plus 80, so that is 240. So mg into 80 plus 160, okay, which is equal to 1856, right? Mg we have already found to be 1856 into 240, right? This is 240, 80 plus 160 is 240. So which will give you 445,440. Okay. So SB2 into 160, right? SB2 into 160 is equal to 445,440. So SB2 is equal to 445,440 divided by 160, which will give you 2,784 Newton. Okay. So SB2, this force at this spring at this position is 2,784 Newton. Okay. Now we have to find the stiffness of the force, stiffness of this spring. All right. When the sleeve rises 0.15 meter, 0.015 meter, the extension in spring B. Okay. So we need to calculate first when the sleeve, this one rise up 0.015 meter, how much would be the change here on B? Okay. So since there's a lever, 0.015 into 160 will be equal to 0.1 into, sorry, 0.01 into 160 plus 80, that is 240. So when you solve it, you will have this SB2, right? SB2, this extension and spring B will be equal to 0.015 into 160 divided by 80 into 80 plus 160, right? So when you solve it, you will have 0.01, right? So this is simple lever, right? Simple lever we are calculating. If this much is the extension here, how much will be the extension here, right? That's what we have calculated. So that is 0.01 meter. So the extension at spring B will be equal to 0.01 meter, that is 10 millimeter. Okay. So now we have to find the stiffness of the spring B. That's what the question is. How do we find it? We already have the stiffness, or not stiffness, the spring force of B at maximum position. We have the spring force of B at minimum position. We know the extension of spring B between these two, right? So we can calculate the stiffness. How much is the stiffness? Stiffness is the ratio of, not ratio, stiffness is the spring force divided by the extension, right? Why? Stiffness into extension will give you the spring force, which means spring force divided by the extension will give you the stiffness, right? So spring force we have 2,784 for maximum position minus 2,529 for minimum position, right? 2,529 for minimum position. So A minus B upon extension, that is 0.01. So you can find this is equal to 25,500 Newton per meter, right? 25,500 Newton per meter. So that's the stiffness of this spring. Okay, spring B, 25,500 Newton per meter. So when you convert it into Newton per millimeter, you will have 25.5 Newton per millimeter, right? So this is the stiffness of this spring.